Hey y'all, welcome back to my channel. My name is Jeffrey. In this video I'm going to discuss some action potentials in your heart. Okay, so the two different action potentials I'm going to talk about are going to be your nodal cells, which are also called your pacemaker cells. So remember, your pacemaker is going to be your sinoatrial node, your SA node, or your atrioventricular node, your AV node. So these nodal cells are actually going to be connected to these other contractile cells via gap junctions. So the contractile cells are going to be the second type of cells that I'm going to talk about in your heart. These are going to be called myocytes. Okay, so your nodal cells are actually going to dictate how strongly these myocytes are going to contract and how fast they're going to contract. And your myocytes are going to have their own action potential and how they propagate contracting. Okay, so these two different cells in your heart are very, very important, which is why we're going to dive right in. So for your nodal cells, on your y-axis you're going to have your millivolts, and these are going to be your resting membrane potential is going to be anywhere from -65 to about -80, and this is going to be 0 right here. So your nodal cells are going to have action potentials in 3 different stages. Okay, so the first is going to be kind of your slow depolarization phase, and then that's going to be split into 2 parts, and then we're going to have that rapid depolarization phase past that 0 millivolt mark, and then we're going to have kind of that rapid repolarization phase so that we can repeat this cycle. And remember, your pacemaker is usually your sinoatrial node, and your SA node is going to be sending these signals, roughly 60 to 80 beats per minute. That's the average for the human heart rate. Okay, so we talked about these 3 different parts of your action potential. So let's dive into what all of these components are. Okay, so for your for the A here, these are going to be also known as your funny sodium channels. So these are going to actually lead to a very slow depolarization of your cell, as it's kind of constitutively active and allows for sodium to come into the cell from the extracellular space. Okay, B is going to be your T-type calcium channels. Okay, and these are also a very slow depolarizer. Okay, so it's going to allow for calcium ions to come into the cell. Now, about at this point we're going to say it's -40 millivolts, and that's also going to be our threshold potential, allowing for the second type of channel to open, and allowing for the second part of our action potential. Okay, so these are actually going to be called L-type calcium channels. Okay, these L-type calcium channels allow for a very quick, a very fast depolarization, as you can see from the actual graph itself. And then finally, obviously, all depolarizations must come to an end. You have to get back to that resting stage, which we're going to have these delayed rectifier potassium channels open. Okay, so when these potassium channels open, remember, our potassium ions are greater inside the cell than outside, so when they leave, that's going to make our cell more negative. So these delayed rectifier potassium channels allow for our action potential to go back down, and then so that we can repeat the process over and over and over. Okay, so now that we kind of know about these nodal cells, basically we have these all of these channels right on the membrane, right, and they allow for all of these cations to go into the cell. Now we have these gap junctions right here that are going to be connected to our myocytes. Okay, so our myocytes don't actually have this kind of intrinsic property, such as the T and the funny T-type calcium and the funny sodium channels. They kind of rely on these gap junctions for their initial depolarization. Okay, so on the myocytes, they're going to be a little bit more negative, right? So these are going to actually be, the resting membrane potential is actually going to be around -85 millivolts, as opposed to, about 70 millivolts or so. And then we're going to have a -70 right here, and then as well as that 0 that we had before. Okay, so this initial depolarization that we have to -70 is actually going to be due to these gap junctions as the ions rush into the myocyte from those gap junctions. So this initial stage right here is going to be due to our nodal cells, okay? And then once we reach -70, that's actually the threshold potential. Okay, so once it reaches threshold, we're going to have these voltage-gated sodium channels opening. That's going to allow for a rapid influx of sodium. So this is going to be the first stage of our action potential. And then once we reach about -20 or about +20 millivolts, we're going to have our voltage-gated potassium channels open. So that's going to allow for that kind of repolarization for a bit up until 0 millivolts, which is where we have our L-type calcium channels open, and those cancel out the effect of the potassium channels. So then we're going to have kind of a relatively no change at 0 millivolts, and then finally we're going to have our delayed rectifier potassium channels open, and we're going to go back to about that -85 mark. Okay, so this is going to be the second part, this is going to be the third part, and then we have that final part. So just putting it in writing on what I just said, we're going to have our voltage-gated sodium channels. It's going to be a very fast depolarization. And then we're going to have our voltage-gated potassium channels opening, which is going to be very fast repolarization. But then at point 3, we're going to actually have our L-type calcium channels opening, and that's going to lead to a very fast depolarization as well. But these two are going to cancel out, so that's going to even out our action potential here. And the calcium is actually the reason why these action potentials for the cardiac myocytes are going to last so long. Okay, because we're not going back down for a period of time, which is anywhere from 250 to about 350 milliseconds. It's usually around 300 milliseconds for an action potential for a myocyte. Okay, and then the very last part is going to be our delayed rectifier potassium channels opening, and that's going to lead to our kind of rapid repolarization back to -85 so that we can repeat this action potential over and over again. Now, these are very long action potentials. So compared to skeletal muscle is actually going to be anywhere around 10 milliseconds or less. Okay, so it's going to be a lot longer for these cardiac cells. Okay, so that is going to be the rundown of your cardiovascular system electrophysiology. Have a great day.